In this tutorial, we are going to learn different ways to express the concentration of a solution, as well as begin to learn some strategies to solve problems involving concentration expressions. But before we do that, I want you to have or gain a bit of an understanding as to what concentration actually is. To put it simply, concentration is the amount of stuff in a given volume or in a given space. But we can use terms that are maybe a little bit more technical than that, and so we're going to talk about the amount of solute per amount of solution. And so concentration is the amount of solute, which is the stuff, in a given amount of solution. And if we take a look at figure 1, we can talk a little bit about the different components of a solution. And so we said that you've got the solute, and that's the stuff that is dissolving in the solvent, and the solvent is the stuff that's doing the dissolving. And together those two things form the solution. And you can have a dilute solution, or you can have a concentrated solution, and that just deals with the amount of solute that you have dissolved in that solution. And so a dilute means you have a small amount of solute, and a concentrated solution means you have quite a bit of solute. And in fact, if we look at figure 2, we can see how we start with a dilute solution, but as you add more of the solute, the copper sulfate, the concentration increases, and we can see that from the growing intensity of that blue color. And eventually you reach a point where no more solute can dissolve in the solution, and that's of course when we have a saturated solution, which we talked about in the solubility curve activity. The first type of concentration expressions that we're going to talk about are the percent concentration expressions. And you'll see that there are mass-volume expressions, mass-mass, and volume-volume. And the reason why we have these different ways to express concentration has to do with the form or the state of both the solute and the solution. For instance, in a percent mass volume, you've got the mass is if you have a solute that is in the solid state. And so you would measure the mass in grams, and the volume is the solution is in a liquid state, and you measure it in milliliters. And so with the mass percent, you've got both solids, and so you're measuring both in grams, and then the volume, you've got both the solute and the solution are liquids, and so you are measuring those things in milliliters. The other thing is that it's a percent, and so in each case we've got that it's out of 100, and so that's why we have the grams of solute per 100 milliliters of solution, because really the translation or the meaning of percent is out of 100. And so in the mass volume percent, it's saying that you have a certain number of grams of solute for every 100 milliliters of solution. In the mass percent, it's saying you have a certain number of grams of solute per every 100 grams of solution. And then with the volume percent, it's a certain number of milliliters of solute per every 100 milliliters of solution. And when we write these concentration values down in this form, we include I call them the units, but we write the percent MV or the percent MM or the percent VV after the numerical value, just to be clear as to what form of the concentration expression we're using. So for instance, you may have noticed before on a jug of vinegar that it says it's a 5% solution, or a 5% volume solution. Well, that volume refers to the fact that you've got both your solute and your solution in the liquid state, and since vinegar is a solution of acetic acid mixed with water, that makes sense. But more specifically, it's saying that for every 5 milliliters or 5.0 milliliters of your solute, your acetic acid, that's how much occurs in 100 milliliters of solution. Or if I had 100 milliliters of the vinegar solution, I would have within that 5 milliliters of the acetic acid that was dissolved. And if instead of vinegar, let's say we had a mass percent, then that would be for every 5 grams of the solid solute that is dissolved, you would have 5 grams of the solid solute in 100 grams of the solution. And an example of that would be in a metal alloy where you've got a small amount of metal that is dissolved, or maybe better mixed with a larger amount of metal, and the smaller amount acts as your solute, and the smaller amount acts as your solute, and the larger amount acts as your solvent, and together they make up that solution. And as far as the formula and strategies column and you filling that out, as far as that all goes, I've tried to give you a way to interpret what these different expressions mean by connecting the solute to the solution in the different forms. You'll see that in your textbook there are formulas that you could use that you may prefer to use to help you work through these problems. Either way, it is up to you. It's whatever you're most comfortable with. But when I am solving the problems in the next tutorial, you'll see me using either this approach, or this approach, depending on the information that is provided. Sometimes we need to measure concentrations of things that are really, really small. There's a really, really small amount of solute per amount of solution. And that's where the part per million or parts per million and parts per billion come in. To give a little background first before we talk about how to solve an expression or how to use the information in a ppm expression. The idea of a part per million, so it says that a milligram is 1 ppm of a kilogram. So there is, in 1 kilogram, there are 1,000,000 milligrams, and so 1 milligram would be 1 part of those million parts. To justify that, or to talk about that in another way, so it says, in the context of dilute aqueous solutions, a liter of water has a mass of 1,000 grams, or 1,000,000 milligrams, as I mentioned. And so if you have 1 milligram of solute in 1 liter of solution, that is 1 part per million. If you have 1 milligram of solute in 1,000,000 milligrams of solution, that is 1 part per million. And so if we look down here, we can come up with some units, maybe some units that we are maybe more able to measure, or can more readily measure, and use those units to express a part per million. So if you have 1 milligram per liter, you've got 1 part per million. If you've got 1 microgram per gram, and a microgram is 1,000 times smaller than a milligram, as seen up here, you've got a part per million. Or if you've got 1 milligram per kilogram. And for me, the two units that you definitely want to remember, or that are equivalent to 1 part per million, is 1 milligram per kilogram and 1 milligram per liter. And likewise with 1 part per billion, it's the exact same idea, it's 1,000 times smaller. So instead of having 1 milligram per liter like you do in 1 part per million, you would have 1 microgram per liter, and that would be equivalent to 1 part per billion, or 1 microgram per kilogram. The nanogram per gram, you're probably never going to use that, but it's there so you see it. Again, the key ones that you want to know that are equivalent to 1 part per billion are 1 microgram per liter and 1 microgram per kilogram. And just to give a little bit more context about just how small a part per billion is, if you add a pinch of salt to a 10-ton bag of potato chips, that's like 1 part per billion. And again, just like before, for the formula or the strategy part, there are formulas in your textbook that you can use, that you can sub the information in. But what I'm going to use when I solve these problems, and you'll see in the next tutorial, is this concept, let's say for a part per million, that the 1 milligram per liter represents the fact that you have 1 milligram of solute per liter of solution, or you have 1 milligram of solute per kilogram of solution. We can make those units, or those expressions, equivalent to 1 part per million. And the final unit of expression that we will talk about is molar concentration. And there you see that concept of moles again. We're incorporating, or we're connecting moles to represent the amount of solute that we have. And of course, then the liters will be the volume of solution. And so here, C is the concentration, and N is the number of moles, and V is the volume of solution. And the units, we've got moles, obviously for the number of moles, and liters for liters. So we've got moles per liter. We're seeing how much stuff we have in that solution in units of moles per liter. And this unit of concentration expression will be most important for us, definitely when we are examining the relationships, the stoichiometric relationships that exist between or within solutions. So in this tutorial, we have seen a number of different ways to express concentration, and we see that it all revolves around the amount of solute per the amount of solution, and the different ways just express the same information slightly differently. In the next tutorial, we are going to see how we can apply some of the ideas shown here to actually solve problems and work with different concentration expressions.